Now we are going to another important definition. So, suppose I is a part of R. I is a part of R. Where I is an, what is I? I be an interval. This is an interval. I is a part of R and I is an interval. And C is not an endpoint of if I equals closed interval AB, if I equals closed interval AB, then choose C. Choose C such that C is not an endpoint of I. Means C lies in between this AI. Then suppose f is an increasing function. If you define a function f from I to 1, where f is increasing, f is an increasing function, then we are going to a definition. Then jump, J-U-M-P, then jump of f at this C. What is C? C is not an endpoint of this I. That is a crucial point here. Jump of f at C, which is denoted by JF of C. This is jump of f at C, JF of C. And which is defined as this JF of C equals f of C plus minus f of C minus. JF of C is f of C plus minus f of C minus. This is an important result. This is the important definition. This is the jump of f at C. What is f? F is an increasing function which is defined from an interval to set of reals, and the C is not an endpoint of the given interval. Then the jump of f at that point C is denoted by JF of C and is defined as it is f of C plus minus f of C minus. With the help of the previous theorems, we redefine this function. That is JF of C equals, we know what is f of C plus? F of C plus is, it is limit x tends to C plus f of x. Minus, what is f of C minus? It is limit x tends to C minus f of x. Also, by the previous theorem, we know that JF of C is, what is the limit x tends to C plus f of x? We already proved that is nothing but infimum of f of x, where x following I with x greater than C. Minus, what is the next quantity? Limit x tends to C minus f of x is, it is supremum of f of x, where x following I with x less than C. So this jump of f at C, where C is not an endpoint of the given interval and f is an increasing function, then JF of C, the jump of f at C is defined as in this way. It is infimum of f of x for all x following I with x greater than C, minus supremum of f of x where x following I with x less than C. So this is the jump of f at C. Okay. Now, from this definition, suppose if C is an endpoint, C is a left endpoint, that is I equals closed interval AB, I is closed interval AB, and C is the left endpoint. If C is the left endpoint, it means if C equals A. If C is the left endpoint, that is C equals C, then JF of C is defined as, instead of C, it is C. JF of A or JF of C, simply. JF of C is, if C is a left endpoint, then JF of C is limit x tends to C plus f of x minus f of C. If C be the left endpoint, by using the definition, C is nothing but the endpoints of I. But here, if the special case, if C be the left endpoint, that is C equals I, so JF of C is limit x tends to c plus f of x minus f of c. That is some jf of a. You can replace the c by a. It is limit x tends to a plus f of a. Limit x tends to, a plus f of x, not f of a plus f of x minus f of a. When c be the left hand point, then jf of a is limit x tends to a plus f of x minus f of a. When c be the right hand point, that is the second case. If c be the right hand point, c equals b, what happens? Then jf of b like this equals f of b minus limit x tends to b minus f of x. So these are the two special cases. If c be the left hand point, that is c equals ca, then jf of a is limit x tends to a plus f of x minus f of a. And if it is right hand point, then jf of b is f of b minus limit x tends to b minus f of x. Clear? Moreover, j of c, this is the jump of f at c when c is not an endpoint of the given interval, and for the increasing function f, jump of f at c, jf of c is nothing but f of c plus minus f of c minus. Okay. Now there is an interesting result. So we are going to a theorem, that is, if I is an interval, I is a part of I is an interval, it is interval, let f from I to on, you can define a function f from I to on with f is increasing. F is an increasing function, f from I to on, where f is increasing on I. F is increasing on I. If C fall in I, C fall in I, C fall in I, what is I? I equals closed interval AB. C fall in I means either C is the left hand point, or C be the right hand point, or C may be lies in between this A and B. Maybe it is A, maybe it is B, or maybe it is differs from A and B, but it lies in between A and B. Okay. So if C fall in I, then f is continuous. If f is continuous at C, if f is continuous at C, then j f of c equals 0. If f is continuous at c, then j f of c equals 0. So when f is not continuous, so j f of c differs from 0. If f is discontinuous at c, surely j f of c differs from 0. If f is continuous at c, then the jump of f at c should be 0. There is no jump. That's the meaning. That is the meaning means, that is the meaning of continuity. Okay. How to prove this one? So there are three cases. Why? Because C is in I. Because C is in I. First case, C is lies, C is not an endpoint. Case first. C is not an endpoint. C is not an endpoint means C lies in between A and B. A less than, C less than. This is the first case. C is not an endpoint. C is not an endpoint, and given f is continuous at C. F is continuous at C. F is continuous at C means surely it is f of c plus equals f of c minus. This is by the definition of continuity. F of c plus equals f of c minus equals f of c. Okay. But what is jf of c? When c is not an endpoint, we know that jf of c is f of c plus minus f of c minus. But here since f is continuous at c, we know that f of c plus equals f of c minus, but for f of c plus minus f of c, surely this is different. They are equal. Why? Because of the continuity of f at c. So when c is not an endpoint of the given interval, j of c should be 0. That is what we require here. So the first case is over. Clear? Okay. Go to the second case. What is the second case? Second case, case second. C is left endpoint. C equals E. That is, C be the left endpoint. Left endpoint of I. C be the left endpoint of I. Also we know that f is continuous. F is continuous at C. That means f of c plus equals f of c minus equals f of c. Okay. But we know that if c be the left endpoint of I, what is the f of c? The jump of f at c is, when it is the left endpoint, then the j of c is limit x tends to c plus f of x minus f of c. Okay. But since f is continuous at c, limit extends to c plus f of x. That is nothing but f of c plus. Okay. So this is nothing but f of c plus minus f of c. But what is f of c plus? That equals f of c. Why? Because of the continuity of f. So this should be equal 0. So the second case is also over. Now we are going to the third case. What is the third case? When c be the right endpoint. C be the right endpoint means the jf of c is nothing but it is f of c minus f of c minus. Okay, but if we have f of c minus is same as f of c, it is also 0. So in either three case, j of c equals 0. That is, for a continuous function, f which is increasing, then the jump of f of c and jump of f at c is always 0. Jump of f at c is always 0 only when f is a continuous function, so which is an implies and is implied relation. Okay, necessary and sufficient part are finished here. Why? Because they are one implies each other. Agree. Thank you.